The machine stopped.
For how long?
Not long enough for the report.
What happened?
The operator corrected it.
And then?
It stopped not long enough for the report again.
So nothing major happened.
Repeatedly. So think about what is actually happening on a factory floor right now. Or, I mean, frankly, inside any kind of complex, high-volume environment.
Right, like any automated system.
Exactly. You have these, multi-million-dollar automated systems. You've got dashboards just glowing with green lights, and executives looking at these output reports that basically suggest everything is running perfectly.
But it's an illusion.
Yeah, totally, because down on the floor, a human being is reaching their hand into a machine every, 4 minutes to clear a slightly skewed piece of cardboard, or resetting a sensor, and then they step back just in time for that green light to stay on.
Right. They are acting as the system's shock absorber.
Exactly. So today, we are doing a deep dive into this hidden manufacturing bottleneck, the world of small production stops, or what the industry often calls micro-stops.
And to really ground this conversation, we are pulling from a remarkably insightful stack of operational sources today.
Which is great, because we don't want to just guess here.
Right, no guessing. The foundation is this document called Field Note number 013, which is titled, Why Small Stops Disappear from Big Reports.
Great title, by the way.
It really is. And we're combining that with some really rigorous operational analyses from groups like Index, Expletia, and Sage Clarity. Plus, we are anchoring the whole thing in the established total productive maintenance frameworks, the TPM frameworks provided by Vorn.
Perfect. So the mission for you, the person listening to this right now, is entirely practical. By the time we finish this deep dive, you should be able to walk onto a shop floor and just immediately recognize a small stop pattern.
You'll see it everywhere once you know what to look for.
Oh, absolutely. And you should be able to explain exactly why these incredibly disruptive events manage to completely escape the formal reporting systems that, your company probably paid millions of dollars for.
Right. We are also going to introduce a very simple machine-side tick sheet.
Yeah, using categories that actually make sense to the people doing the physical work, not just the engineers.
Crucially, yes. And we will detail how to review those counts to select repeated events for closer study.
And we're going to outline how to do all of this without asking the operators to do unnecessary mathematical calculations during their shift.
Or, and this is so important, without ever using this data to rank or evaluate the people running the machines?
Yeah, right. Because the absolute second this turns into a performance review, the data just disappears.
It evaporates.
Exactly. But before we get into the psychology of the operator or, designing that tick sheet, we need to draw a very clear box around what we are actually talking about here.
We need to define a small stop.
Right. Because if I go to, say, 3 different plant managers right now and I ask them to define a micro stop, one of them is going to tell me it's any stop under 1 minute.
Sure. Very common.
Right. But then the next one says it's anything under 3 minutes. And the third one says 5 minutes. It just drives me crazy. Are we just making up arbitrary time thresholds depending on what makes our end-of-month charts look better?
Well, honestly, yes. And that is the exact trap that most organizations fall into. The sources, especially the Vorn material, they explicitly warn against doing that.
Oh, they do?
Yeah, because trying to pin down a universal threshold, whether that's in seconds or minutes, it entirely misses the fundamental nature of the problem.
Okay, so how should we look at it?
If we synthesize the frameworks from the sources, a small stop is not defined by a stopwatch. It is defined by its characteristics.
Okay, that makes sense. So if we are throwing out the universal stopwatch, what are those defining characteristics? What am I actually looking for if I'm standing on the floor?
There are essentially 5 core characteristics to look for. First, yes, it is brief. We are generally talking about seconds or maybe a handful of minutes, not hours.
Right, it's quick.
Second, and this is the mechanical differentiator here, it is recovered without major maintenance intervention.
Meaning what, exactly?
Meaning the operator does not need to get on a radio and call a specialized technician. They don't need to lock out and tag out the main power source to, completely tear down the gearbox.
Oh, gotcha. So they aren't unbolting safety guards and pulling out giant wrenches.
Exactly. Which leads directly to the third characteristic. It is restored by a routine operator action.
Just a normal part of their day.
Right. It's a physical intervention that the operator can perform safely and quickly as just a normal part of their standard operating rhythm.
Okay, what's the fourth one?
Fourth, because of those first three factors, it falls entirely below the normal reporting threshold of the facility software.
Because it's too fast and too routine for the computer to care.
Precisely. And fifth, while one single instance of this stop is incredibly easy to just dismiss as a random fluke, it becomes highly operationally relevant and actually very destructive when it is repeated.
Okay, I want to challenge this a little bit against the traditional frameworks. Because as a practitioner, I look at the total productive maintenance principles, like the classic TPM stuff from Vorn.
The six big losses.
Exactly, the six big losses in manufacturing. Where does this, 15-second sensor reset actually live in that taxonomy?
Well, in the Vorn framework, these events are classified under idling and minor stops.
Okay, idling and minor stops.
Right. But here is the critical mechanistic nuance, and honestly, it is the exact reason why these stops fly completely under the radar of upper management.
I'm listening.
When a factory calculates its overall equipment effectiveness, its OEE, these minor stops are mathematically categorized as performance losses, not availability loss.
Whoa, okay, I need to stop you right there. We cannot just throw around terms like performance loss and availability loss without explaining the actual mechanics of the math.
Fair point. It's a crucial distinction.
Let's break this down for everyone. If I am running, say, a bottling line, what is the difference between those two buckets, and why does that specific difference make microstops invisible to the plant manager?
Okay, let us walk through the calculation mechanics. Availability loss is binary, and it is very dramatic. The machine is scheduled to run, but it has completely starved.
Like it's broken.
Right. A main drive belt snaps. The line goes dead. It takes a maintenance crew 60 minutes to replace that belt. For that entire 60 minutes, the reporting system logs 0 availability.
So it's literally just a massive red block on the daily shift chart.
Exactly. Everyone knows it happened. The maintenance manager is writing an incident report. People are asking questions.
Okay, so that's availability loss. What about performance?
Performance loss, on the other hand, measures something entirely different. Performance assumes the machine is available, but it is not running at its ideal maximum theoretical speed.
Oh, I see where this is going.
Let us say your bottling line has an ideal cycle time of 100 bottles per minute. If you run for 60 minutes, you should theoretically produce 6,000 bottles.
Basic math, sure, 6,000 bottles.
But at the end of the hour, you only have 4,500 bottles.
So I am missing 1,500 bottles. Where did they go?
Well, the system algorithms look at the data. They see no major breakdowns, no belt snapped. There is no recorded availability loss.
Right.
Therefore, the algorithm makes a mathematical assumption. It says the machine was available for the full hour, but it must have been running slowly. It registers a speed loss.
Oh, wow. So the system literally misdiagnoses the reality of the floor. It looks at the missing 1,500 bottles and just assumes the machine was casually cruising at 75 bottles a minute instead of 100.
Yes, exactly. It completely misses the physical reality, which is that the machine was actually running at a blazing 100 bottles a minute, but it completely stopped for 15 seconds, a dozen different times, because maybe a label kept peeling off and jamming a sensor.
That is a phenomenal blind spot.
It's massive.
If I can offer an analogy here, it's like using a really poorly programmed GPS tracker on a delivery truck.
Okay, I like this.
Let's say the GPS is designed to only register a stop if the truck's engine is turned off for more than 5 minutes.
So that is your availability loss threshold.
Right. So the driver does a route across a busy city. They're driving at 50 miles per hour, but they hit, 30 different red lights. At every red light, they just sit idling for 45 seconds.
Right, the engine is still on.
Exactly. So at the end of the day, the dispatcher looks at the GPS data. The GPS says, hey, the engine was never turned off for more than 5 minutes, therefore the truck never stopped.
But the route took 2 hours longer than it should have.
Yes. So the dispatcher concludes, wow, this driver must have just been driving 15 miles per hour the entire day.
That is a mechanically perfect analogy for misattributed performance loss. The dispatcher, or in our case, the plant manager, is trying to solve a speed problem that simply does not exist.
Because they are completely blind to the fact that they actually have an interruption problem.
Exactly. And think about the operational reality of setting arbitrary time thresholds based on that flawed assumption. If a plant has a manufacturing execution system, an MES, that is hard-coded to ignore any downtime event shorter than 3 minutes, they are living in a fantasy world.
And they really are.
Ah.
Let's construct a really specific illustrative example here just to drive it home.
Sure.
You have an automated case erector, right? It takes flat pieces of corrugated cardboard and folds them into boxes. But today, it's super humid. The cardboard has a slight warp to it.
A very common environmental variable. Material handling is heavily affected by that.
Right, humidity changes everything. So the suction cups on the robotic arm grab the warped cardboard, and one out of every, say, 50 boxes doesn't seat properly in the folding rails.
So it jams.
Sort of. The machine's internal sensors detect resistance, and to prevent tearing itself apart, the PLC, the brain of the machine, triggers an immediate safety halt.
So the red light flashes.
Exactly. The operator walks over, opens the Perspex door, pulls out the crumpled cardboard, resets the fault on the touchscreen, closes the door, and hits start. The whole physical intervention takes, 45 seconds.
It is a textbook minor stop. Brief, routine, safely handled by the operator.
But because it only took 45 seconds, the MES system, with its 3-minute threshold, just throws that data out. It effectively never happened.
It is invisible to the software.
Right. Now, let's say that humidity persists all day, and that 5-second misfeed happens 60 times over an 8-hour shift.
Well, you have just lost 45 minutes of pure production time.
Almost an entire hour of capacity just evaporated. And yet, if the plant manager pulls the downtime report for that case erector the next morning, that column is completely blank. The official report says 0 downtime.
The machine is heralded as a paragon of reliability.
It's madness.
Oh.
Which is exactly why the Vorn sources emphasize that these minor stops represent a classic hidden factory loss.
Yes, the hidden factory. The facility has a theoretical capacity, but a massive percentage of it is being quietly consumed by these micro events. The loss is happening, the time is evaporating, the financial impact is very real, but your formal measurement tools are structurally blind to it.
This brings us directly to the core investigative question of this entire analysis. If the financial impact is so high, and if we know we are missing production targets, why do these massive, expensive reporting systems continue to miss small events?
It's a great question.
I mean, we touched on the program time thresholds, the 3-minute rule, but it goes so much deeper than just a line of code in the software. Why does the human system miss it?
The sources outline a multitude of investigative possibilities for this, and we need to look at them systematically.
Okay, what's the first one?
First, and perhaps most obviously, the event simply ends too quickly for the traditional management apparatus to react.
What do you mean?
Well, by the time a supervisor notices the flashing light at the end of the aisle and starts walking over, the operator has already cleared the jam. The line is moving again.
Right. The visual evidence of the failure has literally been physically removed and thrown into the recycling bin.
Exactly. The crisis is averted before it can even be observed by management.
That makes total sense. What's next?
Second, formal reporting naturally and structurally gravitates toward larger losses. A 45-minute breakdown is an undeniable high-visibility crisis.
Oh, for sure. If a main drive motor burns out, it's chaos. A maintenance crew is scrambled, spare parts are being sourced from the warehouse, the production planner is frantically rescheduling orders.
And the plant manager is pacing the floor asking questions.
Yeah, it's an event with a massive blast radius.
Yes, and the reporting system is meticulously built to capture the forensics of that blast radius. It wants the breakdown duration, the time it took maintenance to respond, the time it took to actually wrench on the machine, the time it took to power back up.
It wants all the details.
Because the system is hungry for big data about big events, it simply lacks the granularity to care about a 45-second crumpled box.
Okay, but let me push back on that a little bit. Why couldn't we just ask the operator to write down every time they clear a box? If the software can't catch it automatically, why can't the human just tell the software it happened?
That brings us to the third investigative possibility. Exact timing is incredibly difficult during a physical recovery.
Because they're busy.
Exactly. We have to consider the cognitive and physical reality of the human being running the machine. If an operator is trying to safely clear a jam from a moving conveyor system, they are not looking at their wristwatch to note that the stop started at exactly 10.14 and 32 seconds.
Right, their hands are inside a machine. They're looking at pinch points, they're looking at tensioners.
Their entire cognitive focus is on the safe restoration of flow, and this connects directly to the fourth reason. Event coding is a massive administrative burden.
Oh, I hate downtime coding.
It's rough. Even if the operator somehow managed to mentally log the exact second the machine stopped, what do we ask them to do next? We ask them to step away from the machine, walk over to a digital terminal, log in with their RFID badge, open a drop-down menu with 60 different downtime codes, select minor jam zone 4 in feed, and type in a duration.
Which takes, what, 2 minutes to do? You're asking them to spend 2 minutes doing data entry to document a 45-second physical fix.
It is entirely disproportionate. Operators, quite rightly and rationally, prioritize restoring flow over completing administrative paperwork for a minor event.
That is so true. But the fifth reason, this is the one that really gets under my skin as someone who studies operational culture.
The psychological element.
Yes, it is the normalization of deviance. Think about the life cycle of an operator. You start a new job on a packaging line. On your first day, the machine jams every 20 minutes. You're super frustrated. You complain to the supervisor. You ask maintenance to look at it.
You view the stoppage as an anomaly that needs to be solved.
Right. But maintenance comes over, they look at it, they shrug, and they say, yeah, the cardboard is cheap today. It just does that. Just keep clearing it.
So you adapt.
Exactly. Fast forward a year. You don't complain anymore. You don't even think about it.
Yeah.
The act of reaching in, pulling out the jam, and hitting reset has become pure muscle memory.
Yeah.
It is no longer an interruption to your job. It actually is your job.
It has become the background noise of production.
Yeah. You don't report it because you don't even perceive it as a failure anymore.
So the machine is recorded as running,
Yes?
and the operator keeps correcting it.
Yes.
That feels like running with additional personnel.
It absolutely does.
Yeah.
You are essentially taking a highly skilled human being whose brain should be focused on quality control and process optimization, and you are using them as a physical patch for a machine's mechanical instability.
Yes.
You're using human labor as a shock absorber for bad equipment.
This dynamic is exactly what the Index source brilliantly conceptualizes as the availability illusion. It is a profound operational trap.
Okay, let's break that down. How does that illusion actually manifest in the real data?
Picture the operations director. It is Friday afternoon. They pull up the weekly performance dashboard. They see that line 3 had 92% availability this week. The dial is green.
Looks great.
They think, fantastic, we had almost no downtime. The maintenance team is doing a great job. But that 92% availability only reflects the absence of major breakdowns. It only includes the events that were long enough to cross that arbitrary 3-minute threshold we talked about.
So the illusion is the belief that for 92% of the week, the machine was just humming along continuously without any interruption.
Precisely. The director sees a solid block of green time, but if you were to zoom in with a microscope on that green block, you would see it is actually completely shattered. It is fractured by 200 tiny, undocumented microstops. The machine was technically available, but it was highly unstable.
Which feeds right back into that misattributed performance loss we discussed earlier. The director sees the high availability, then looks at the total output, sees they missed their production target by 10%, and assumes the machine is just running slowly.
And what is the standard management reaction when they think a machine is running slowly?
They tell the operator to turn up the speed dial.
Exactly.
Which is the worst possible thing you could do, because if a machine is jamming every 20 minutes at 100 units a minute, turning it up to 120 units a minute is just going to make it jam every 10 minutes.
Yeah.
You are literally pouring gasoline on a fire you can't even see.
We must be very clear about the potential scale of this blind spot, by the way. According to studies conducted by the Polish Association for Production Management, which were cited in the Explusia source material, this micro downtime can constitute 50 to 60% of total downtime.
I have to pause there.
Yeah.
50 to 60%.
Yes.
More than half of all the downtime happening in a facility could be made up of these invisible little stops.
It is possible, yes.
Yeah.
Now, I must state an absolute requirement here. The local frequency and operational effect must be measured.
Right, we aren't painting every factory with the same brush.
Correct. We cannot irresponsibly assume that every single factory in the world is losing 60% of its time to microstops. The exact percentage will vary wildly based on the age of the equipment, the quality of the raw materials, and the nature of the specific process.
Fair enough, I get that. But even if it's only like 20% or 30%, the magnitude is just staggering. If a massive chunk of your capacity is quietly bleeding out through 1,000 tiny cuts, and your expensive software can't even see the cuts, you are flying completely blind.
Which leaves us with a very pressing question. If the formal reporting system is blind, if the OEE calculations are misattributing the loss, and if the automated sensors are ignoring the data, what sensor do we have left?
Well, the only sensor we have left is the human being standing next to the machine, the operator who's physically recovering the process.
Exactly. The human operator is the ultimate high-fidelity sensor of operational instability. But relying on this sensor introduces a fascinating paradox on the shop floor.
Let's explore that, because the dynamic between the operator and the machine is where this gets incredibly complex. We are saying the operator is the one experiencing these stops. But as we just discussed with the normalization of deviance, they recover them so quickly that the problem effectively vanishes from the official record.
It is what we can call the paradox of competence. Think about what we train operators to do. We train them to be efficient, to be safe, and to keep the product flowing. The better an operator is at their job, the more fluidly they anticipate a jam, the faster they clear a misfeed, the quicker they reset a fault.
They become ninjas at keeping the machine running.
Yes, but their very competence, their speed in recovering the machine, actually hides the instability that is creating the stoppage in the first place.
Wow, that's wild.
The better they are at rescuing the machine, the less likely management is to ever know the machine needed rescuing. The operator is effectively and unintentionally masking the deterioration of the equipment or the variation in the raw materials.
That is a brilliant way to frame it. So, if we acknowledge that the operator's intervention is our only real signal here, what does that signal actually mean? Like if I stand on a catwalk overlooking the floor and I see an operator intervene with a packaging machine 20 times in an hour, what is that a symptom of?
We have to be meticulous here. A repeated intervention may indicate several distinct systemic issues. First, it could be a recurring mechanical condition.
Like what?
Perhaps a localized bearing on a specific roller is starting to fail. It hasn't seized completely, but it is causing occasional friction that skews the material just enough to trigger a sensor fault every few minutes.
Okay, so it's a leading indicator of a major breakdown.
Precisely. Second, it might indicate a poorly understood disturbance in the operating environment. We discussed humidity earlier. Or perhaps the ambient temperature of the factory floor fluctuates in the late afternoon, which subtly changes the viscosity of the glue being used to seal cartons.
Oh, that's a good one.
The machine starts missing seals, and the operator has to manually reject them.
It's an environmental variable the engineers just never accounted for.
Third, it could be an informal adjustment. This is where the operator has, through trial and error, figured out a secret workaround. They realize that if they manually tweak the tension dial on a web of plastic film every 10 minutes, the machine won't snap the film.
Which is terrifying, actually, because if that operator goes on vacation, the person covering their shift doesn't know the secret handshake, and the machine just crashes all day.
Exactly. It creates a false dependency on tribal knowledge. And finally, a repeated intervention might simply be a pattern requiring observation. It might be a complex interaction of variables that we do not yet understand, but the sheer frequency of the stop tells us we need to point a flashlight at it.
This brings us to a central principle of this entire operational philosophy, and it is a concept that every single manager listening to this really needs to internalize. The recovery deserves recognition. The repetition deserves investigation.
I want to reinforce that because it is the absolute foundation of how we solve the microstop problem. The recovery deserves recognition. The repetition deserves investigation.
It completely upends the traditional management mindset, because the traditional mindset says the machine is producing parts, therefore the machine is fine. But if we apply this principle, we realize that output does not equal stability.
No, it does not.
Imagine a highly illustrative visual here. You walk onto a pristine factory floor. You walk up to a massive, beautifully engineered CNC mill or, a high-speed bottling filler. Attached to the main console is this digital display with a bright green background, and in large, bold letters it says, status, running.
Standard display.
Right. But if we were being completely honest about the state of the system, underneath that green text, in tiny little warning font, it would say, operator, frequently assisting.
It is a stark observation of reality. The machine is technically in a running state, yes, but it is entirely dependent on a human being's constant physical intervention to remain in that state.
It's not autonomous at all.
No, it's on life support.
But this is where the practitioner in me starts flashing red warning lights. Because if we tell management, hey, we need to start tracking how often the operator touches the machine, human nature takes over. It can incredibly quickly devolve into a witch hunt.
You are absolutely right, and as systems analysts, we must fiercely protect operators from the inappropriate interpretation of this observational data. This is where many lean manufacturing initiatives fail.
This is so common.
We must re-emphasize to every level of management that recurrence alone does not infer a specific technical cause, and it certainly does not infer human error.
Let's make that super concrete. If an operator clears a misfeed 40 times in a shift, a lazy manager looks at that data and says, Clearly, Dave doesn't know how to load the cardboard hopper correctly. Dave is the problem.
And that conclusion is fundamentally invalid without further evidence. We cannot assume why the misfeed is happening based purely on the count. We cannot assert that it is a bad batch of cardboard from the supplier. We cannot assert that the suction cups are worn out. And we absolutely cannot assert that Dave is a lazy or inattentive operator.
Right.
The only thing the recurrence of the intervention tells us is that the physical condition requires attention. It is a flag on the play. It is not the referee's final ruling.
It is a signal of instability, not a measure of human performance.
Okay.
So if we agree that the operator's recovery work is our best source of information, and we agree not to use it to punish them, the logistical question still remains. How do we actually capture this data?
Because the software can't do it.
Right. And because we already proved that making them fill out complex MES downtime logs for 15-second stops is an administrative nightmare that they will just simply refuse to do.
Which logically leads us to the next operational hurdle. Why not begin with precise downtime?
Yeah, why not?
If management wants data, the traditional instinct is to ask for perfect data. Why don't we just mandate that the operators track the exact minutes and seconds of every single stop on a clipboard?
Oh, man. Let's really look at the immense practical burden of asking an operator to log precise downtime for microstops. We have to simulate the physical reality of what we are actually asking them to do here.
We are asking a lot.
We are asking a human being whose primary responsibility is managing a fast-moving, potentially dangerous physical process to spontaneously become a precision timekeeper.
Let us break down the exact cognitive and physical steps required to log just one microstop accurately using traditional downtime tracking methods.
Lay it out for me.
First, the operator must cognitively identify that the stop has occurred and is not just a standard cycle pause.
Right. They have to actually notice the fault.
Second, they must physically move to the machine and recover it safely. This involves assessing the hazard, clearing the jam, and resetting the logic controller. This is their absolute priority, as it should be.
Of course. Safety first.
Third, after the machine is running again, they have to somehow remember or look at a clock to find the exact start time of the event.
Which they didn't look at when the machine stopped, because they were busy lunging for the emergency stop button to save a jamming gear.
Exactly, so they are already estimating. Fourth, they must note the finish time when production resumed. Fifth, they have to perform a mathematical calculation, subtracting the estimated start time from the finish time to determine the duration.
Okay, that's already 5 steps.
Sixth, they must log into a digital terminal or pick up a complex printed form and choose a detailed alphanumeric code from a taxonomy of dozens of options to classify the fault. And seventh, they often have to write a brief, free text explanation of the event to satisfy the engineering team.
Okay, let's look at the math on that administrative process. The physical event clearing the jam took maybe 15 seconds. The administrative event, identifying the time, doing the math, finding the code, writing the note, takes 90 seconds.
It's completely skewed.
The paperwork takes 6 times longer than the physical recovery.
It is a structurally inverted workflow.
If you mandate that an operator do that for every single microstop, and they have, say, 100 microstops in a shift,
Yeah.
you are not just asking them to do a little extra paperwork. You are literally commanding them to stop running the machine for 2.5 hours a day so they can write essays about how the machine is running. It's absurd.
It is entirely unworkable.
The easiest, most rational decision for the worker on the floor is to look at that system, realize it is actively hindering their ability to do their actual job, and simply choose not to use it. Or worse, just fake the data at the end of the shift.
So we add a form.
A small one.
How small?
Reason in 1 tick.
That may be the first form in the factory to leave before the meeting ends.
It is the absolute truth of operational reality. If the tool is heavier than the problem it is trying to measure, the tool gets dropped. The engineers in the corporate office can design the most beautiful, granular, multi-layered data collection form in the world, but if it takes 90 seconds to fill out for a 15-second problem, it is going straight in the trash can.
This is the core philosophical trade-off we must make to capture microstops. The simplified method we are proposing trades initial precision for the visibility of recurrence.
Let's make sure that lands. We are trading precision for visibility.
Yes. The traditional mindset says, I need to know exactly how many seconds we lost to the nearest decimal. Our method says, I am willing to temporarily give up knowing the exact duration in exchange for finally knowing how many times the machine cried for help. We must prioritize revealing the repetition over calculating perfect durations.
Because if we demand the perfect time up front, the administrative burden ensures we get 0 data. But if we just ask for a tally mark, we at least learn where the bleeding is actually happening. We can figure out exactly how much blood is being lost later.
Precisely. Which brings us to the actual physical intervention. If we are abandoning complex software and precise timekeeping, what does this low-burden tool actually look like? We introduce the machine-side tick sheet.
This is where we get incredibly practical. We are talking about an exercise in restrained design and operational empathy here. We're not talking about an iPad app. We're not talking about an Excel spreadsheet on a terminal. We are talking about a literal piece of paper and a pencil.
It is remarkably low-tech, but the design and implementation rules for this piece of paper are highly specific. If you violate these rules, the experiment will fail immediately.
Let's walk through the design philosophy, because getting this wrong will kill the initiative on day one. I've seen engineers ruin a simple tick sheet by over-engineering it. What is the first principle of designing the categories?
The primary rule is to use local language familiar to the operators.
Give me a mechanistic example of that. What does local language mean versus engineering language?
Let us assume you have a continuous web of plastic film running through rollers. Occasionally, the tension drops. The film wraps around a roller, and it bunches up into a thick, tangled mess. The engineering team might classify this in their documentation as a web tension failure resulting in material accumulation anomaly at transfer point B.
That is a mouthful. No operator is going to scan a sheet looking for material accumulation anomaly.
Exactly. Because on the floor, the operators have been dealing with this for 5 years, and they simply call it a bird's nest, because that is exactly what it looks like. If you want the operator to use the tick sheet, you write bird's nest on the paper. You use their vocabulary, not the vocabulary of the machine manual.
It shows respect for their reality. The second principle ties right into that. Keep the categories mutually understandable.
This is vital for data integrity. If you have 3 different shifts and 5 different operators rotating on this machine, they all need to look at a category and instantly agree on what it physically means.
Because if they don't,
Well, if you use vague catch-all categories like machine fault or process error, one operator might use machine fault every time a sensor needs wiping, while another operator might use it only when a physical jam occurs.
your data immediately becomes polluted and useless. You can't compare shift to shift, which is why we need to provide some illustrative categories. What are we actually talking about putting on this piece of paper?
You want highly specific, actionable physical descriptions. Some illustrative categories might be minor jam, sensor reset, material adjustment, misfeed.
But no matter how smart your engineering team is, they aren't going to anticipate everything, which leads to the third principle.
You must always include an other option or an other recurring interruption category.
Why is that so critical? Because as a manager, I hate the other bucket. It just feels like a cop-out.
It is not a cop-out, it is your discovery mechanism. You do not know what you do not know. The environment is highly complex. If you only provide 4 highly specific options on the sheet and a 5th entirely different undocumented problem starts causing 40 stops a day, the operator has a dilemma. They have nowhere accurate to record it.
So they will either force it into one of the 4 existing boxes, which completely ruins the data for that category, or they will just not record it at all.
Exactly. The other category, especially if you leave a small space for them to write a one-word description next to the tally marks, is how the operator signals to management that the system is failing in a novel way.
The fourth principle is one I have to fight engineers on constantly. Avoid an elaborate taxonomy initially.
Do not build a classification system that requires its own induction program. If a supervisor has to spend 30 minutes holding a training seminar to explain to the operators how to fill out a piece of paper, the piece of paper is too complicated.
It has to be intuitive.
It must be instantly, intuitively understandable. It should require 0 cognitive load. We are asking for 2 things: the reason and 1 tick mark, nothing else.
And the final principle is purely ergonomic, but it might be the most important one for compliance. Placement. Where does this physical piece of paper live?
It must be placed directly at the machine at the operator's natural working height.
It cannot be in a 3-ring binder in the supervisor's office at the end of the hall. It cannot be pinned to a bulletin board across the forklift aisle.
It must be within arm's reach of the physical intervention point. The entire ergonomic flow should be. The operator clears the jam, closes the guard, reaches out their hand, makes a single pencil mark on the sheet, and presses the start button.
Fluid motion.
Yes. The recording of the data must not break their physical operating rhythm. If they have to take 3 steps to reach the clipboard, you will lose 50% of your data.
It's an incredible visual juxtaposition. You walk into a modern factory,
Yeah.
you have a $10 million automated packaging line. It has PLC controllers, servo motors, laser-guided sensors, and it is hooked up to a cloud-based MES dashboard.
Hmm.
And yet, the actual ground truth reality of operational stability, the real data that the complex digital system completely failed to capture, is being faithfully recorded on a 50-cent piece of paper with a number 2 pencil.
It is wonderfully subversive.
It really is.
It is a beautifully elegant, low-tech solution to a high-tech blind spot. However, we must be absolutely clear with management about how this tool is deployed. This tick sheet is a low-cost, low-tech experiment. We strongly recommend running this observation for a defined, limited period, say one specific shift or maybe a single week.
Yes, this is a critical point.
Yeah.
This is not a new, permanent administrative chore for the operator. The goal is not to punish them with a new daily task for the rest of their career. It is a targeted, time-boxed observation. You run it for a week to gather a baseline, to shine a light into the dark corners and illuminate the invisible losses.
And, perhaps most importantly for the integrity of the engineering team, we must strictly reinforce the limitations of this method.
What are the limitations? Like, what can't this piece of paper tell us?
The tick sheet is a first-stage observation method. It records occurrence, how many times something happened, and it records reason, the local category of the fault. It absolutely does not provide accurate total downtime.
Okay, underline that.
Unless time is being separately and meticulously captured, it cannot tell you how many minutes you lost.
So if I am a production manager and I walk into the Friday afternoon executive review meeting, I cannot slap this piece of paper on the table and say, hey, the tick sheet shows 40 minor jams. We estimate a jam takes 1 minute. Therefore, we lost exactly 40 minutes of capacity.
If you do that, you will lose all credibility with anyone who understands statistics or operations. Someone will immediately point out that some of those jams took 10 seconds, some took 45 seconds, and one of them might have taken 2 minutes. You cannot mathematically derive precise downtime from a frequency count without introducing massive margins of error.
You just can't.
You must stay true to what the tool actually measures, which is repetition.
Repetition is the signal. So we have run the experiment for a week. It is Friday afternoon. I walk down to the line and I unclip this piece of paper. It is covered in graphite smudges, maybe a little machine oil, and hundreds of tally marks. What is the next step? How do we transition from simply counting the chaos to actually investigating and solving it?
This is the critical transition phase. We are moving from observation to review. You take the sheet, you tally up the raw counts for each category, and you apply the Pareto principle.
The 80-20 rule.
Right, the concept that 80% of your problems are likely caused by 20% of the discrete causes. You are looking for the vital few, you identify the most frequent recurring cause on the sheet, and you select one repeated event for closer study.
Just one. We don't try to solve all 5 categories at once.
Correct. Focus is essential. During the review process, you sit down with the engineering team, the maintenance team, and critically the operator, and you begin asking targeted questions of the data. First, which interruption occurs most often? Are the tally marks clustered heavily in the misfeed row or the sensor reset row?
Let's say it's the misfeed. We have 150 ticks in the misfeed box for a single week.
Then you narrow the physical geometry. You ask, which machine position is repeatedly involved? Is the misfeed happening at the infeed magazine where the raw material is loaded, or is it happening downstream at the folding rails?
You start looking for correlations, trying to isolate the variables. Like, does the pattern vary by the raw material being used? For example, maybe you notice that the misfeeds only happen on Tuesdays and Thursdays. You dig in and realize that on those days you are running recycled corrugated cardboard, but on Monday and Wednesday you run virgin cardboard. The machine runs perfectly on virgin board, but constantly jams on recycled board.
Exactly. You are isolating the environmental and material variables. Does it vary by the specific product configurations being run? Does the pattern shift depending on which operator is running the machine, which might indicate a difference in setup techniques?
And one of the most revealing questions a manager can ask during this review process is, which temporary adjustment has quietly become standard work?
That is a phenomenal investigative angle. Explain how that manifests on the tick sheet.
Let's say you look at the sheet, and the category for material adjustment has 200 tally marks. That means 200 times this week the operator had to physically reach in and nudge the web of material to keep it tracking straight. Because they do it so often, and they are so good at it, that physical nudge has essentially become an unofficial part of their job description.
Right, it's normalized.
They don't even think about it anymore. But that manual intervention is quietly masking a fundamental mechanical alignment issue with the rollers.
The tick sheet exposes the fact that the human is compensating for the machine's geometric failure.
But this brings us right back to the danger zone we discussed earlier, the psychological safety of the review process. If a shift supervisor who hasn't been trained in this philosophy looks at a tick sheet and sees 80 marks next to an operator station, the immediate knee-jerk reaction in a punitive culture is to point a finger.
It is the natural, flawed instinct.
They look at the data and think, wow, Dave is really struggling this week. He is stopping the machine constantly. He needs to be retrained or reprimanded.
And we must state unequivocally that this interpretation is entirely backward, technically invalid, and highly destructive to operational culture. A high count on the tick sheet is not evidence of a difficult, unskilled, or inattentive operator.
What is it evidence of?
It is evidence of an operator who is repeatedly, diligently, and successfully preventing a difficult, highly unstable machine from collapsing into a large, reportable breakdown.
They are saving the day.
Yes. The high count means they are fighting a constant battle on behalf of the company's output. They are meticulously exposing a systemic problem that the existing reporting software has been programmed not to see.
They are handing management the gift of visibility. They are showing you exactly where your capacity is bleeding out. If you take that gift and use it to hit them over the head during a performance review, you will permanently destroy trust. You will never, ever get accurate, voluntary data from that shop floor again.
The pencils will disappear.
The pencils will disappear,
Yeah.
and the microstops will go back to being completely invisible.
Which leads us to the ultimate framing question for management. When you sit down in that review meeting looking at the Pareto chart of tally marks, you must absolutely never ask, why did the operator stop the machine again?
You must ask instead, why does continuing production repeatedly require this intervention?
Let us contrast those two questions carefully, because the linguistic shift represents a profound shift in operational mindset.
Why did the operator stop again? Assumes that the human being is the primary variable. It assumes the operator is the source of the interruption, the instigator of the failure. It points the finger of blame squarely at the human.
Conversely, asking, why does continuing production require this intervention, assumes that the mechanical process or the material is fundamentally unstable. It assumes the operator is acting logically to preserve the system. One question interrogates the human, the other interrogates the system.
It points a flashlight at the mechanics, not a spotlight at the worker. And once you point that flashlight, the next steps for the engineering team become incredibly clear and highly focused.
Exactly. You have used a remarkably cheap, low-tech tool, a piece of paper, to cut through the noise and identify the priority cause. Let us say the tick sheet proves that a specific optical sensor reset on the ceiling jaw accounted for 60% of all microstops last week.
You didn't ask the operator to diagnose why the sensor was failing. You just asked them to flag how incredibly often it was happening.
Now, and only now, do you deploy your expensive, highly trained resources. The engineering or maintenance team can go down to the floor and observe that specific ceiling jaw sensor with greater precision.
Because now they know where to look.
Right. Now they can stand there with a stopwatch and a digital clipboard to measure the exact duration of that specific fault. They can study the ambient lighting conditions that might be blinding the optic. They can investigate the electrical harness for a loose wire. They can do the deep forensic diagnostic work that they are trained to do.
Okay, we have covered an immense amount of operational ground today. Let's bring this all together. If we zoom out, what is the fundamental journey we have just taken the listener on?
We have charted a path from suffering invisible losses to generating actionable operator-led insights, to synthesize the core takeaways from across all the sources. Big reporting systems, by their very structural design and software programming, are excellent at capturing big stops.
They will accurately log your catastrophic breakdowns, your scheduled changeovers, and your major maintenance interventions.
But small stops survive, and they continuously drain your overall efficiency, precisely because the process, and specifically the human operator, becomes extremely proficient at recovering from them quickly.
The paradox of competence. Because they are recovered so quickly, and because the administrative burden of listing them is so disproportionately high, these microstops fall below the software's reporting threshold. They become the normalized background noise of the factory floor, quietly bleeding away capacity.
But by implementing a remarkably simple, locally understandable tick sheet right at the physical point of intervention, you completely bypass the administrative nightmare of calculating precise downtime.
You stop asking operators to perform mathematics while they're wrestling with a jammed mechanism, and you focus the organization purely on revealing the repetition of the failure.
You trade the illusion of initial precision for the hard reality of visibility. And once you have that visibility, you sit down and review the frequency counts to spot systemic mechanical patterns.
And you absolutely do not use the counts to rank, evaluate, or punish the people running the process.
You use the data to select the most egregious, repetitive event, and you focus your engineering and maintenance firepower exactly there.
It is such a practical, immediately applicable framework. It doesn't require a 6-month software integration project. It doesn't require a massive capital expenditure request to the board. It requires a 50-cent piece of paper, a pencil, and a fundamental willingness by management to actually listen to what the operators are trying to tell them through their daily, repetitive physical interventions.
It is ultimately about giving small stops a measurement methodology that is proportionate to their brief duration, but fully reflective of their massive cumulative impact.
So to wrap up this deep dive, I want to leave you with a final thought to mull over, and it is something that extends far beyond just the manufacturing floor. Look at your own highly automated, optimized processes, whether that is a physical production line, a complex digital workflow in an office, a supply chain routing system, or even a daily administrative software protocol.
It applies everywhere.
How much of your supposedly smooth operation is an illusion? How much of your success is actually just relying on frontline humans performing tiny, undocumented acts of rescue every single day to keep the system from collapsing? What small stop, what tiny manual intervention has quietly become unofficial standard work in your operation?
Because as we've clearly established today, just because the official report says the machine was running perfectly doesn't mean nothing major happened.
It just means it happened repeatedly. Until next time.